Well, hello and thank you for watching. My name is François Févotte. I'm working for a company called Triscale Innov, and I'm going to talk to you about accurate and efficiently implemented sums and dot products. Of course, everything in Julia. This is joint work with Chris Elrod, and everything I'm going to talk about today is freely available in the AccurateArithmetic.jl package, where it reuses previous functionalities that had been implemented by Jeffrey Sarnoff. So, by way of an introduction, this work comes from a nice discourse thread where it was brought to the attention of the Julia community that Python did have this nice fsum function in the standard library that would allow to accurately sum floating point numbers. And Julia at the time did not have any equivalent for that. So Stephen Johnson released this xsum.jl package that wraps the C library of the same name, and it provides exactly rounded sums. And the performance of that was very good, but it did not exploit SIMD vectorization, and so that begged the question whether we could do accurate summations in Julia leveraging SIMD vectorization. And that's actually where the work on compensated algorithms in AccurateArithmetic.jl comes from. So this is what I'm going to talk about, first from a user's perspective, where I'm going to try and explain what accurate means in the context of floating point arithmetic, and especially as a user, why and when you'd like to use more accurate algorithms for your sums and dot products, and what this entails in terms of performance. And then we'll try and take a look under the hood of the package and understand how compensated algorithms work and why and how they can leverage SIMD vectorization, and why Julia is such a nice language to work on such topics. But first we have to understand a bit more about round-off errors and floating point arithmetic and related issues. And well, I think the first thing we all have in mind is what happens when floating point operations are rounded off. An example of that is the following addition, where I'm adding together two numbers that are represented here as 6-digit decimal numbers, and the sum of these two numbers should be that result, that number, and if I want to represent it as a 6-digit decimal number as well, I have to round it off and forget about those last 3 decimal digits. And so, of course, this is a very classical example of a round-off error. And the nice thing about such round-offs is that the relative error that comes from them is always bounded to something like 10 to the minus 16th if I'm working with double precision numbers or 64-bit floating point numbers. And the problem is that this nice property of having bounded relative error is not always, it does not apply to all situations, all issues that can arise with floating point numbers. And one such issue is what we call cancellation, and this occurs when we try and subtract two numbers that are so close to one another that some of the digits cancel out. So let me take, for example, this result from the previous operation and subtract to it the first operand, and I'm hoping to get back my second operand there. But when I'm actually doing this operation in floating point arithmetic, what I'm noticing is that the first 3 digits cancel out entirely, which gives me some space there in the result to store additional information that I cannot compute, because if I wanted to compute anything other than zeros here, I'd have to know about some data that was lost in the process beforehand. So in this sense, this result is very much inaccurate, and the relative error on it is unbounded. It can grow arbitrarily large. And a convenient way of quantifying how and when this happens is to look at this condition number that's defined like so. If we try and understand what this entails for summation algorithms, let's try and look at the simplest summation algorithm that we can think of, which is naive summation, where we have one accumulator in which we accumulate in turn all elements of the vector that we want to sum. A nice graphical representation of this is this kind of scheme where I see that the first two numbers are added together to yield a partial sum to which the third element is added, and this partial sum is updated with each element until in the end it holds the total sum. And we can expect this total sum to be affected by the sum of all round-off errors that occurred beforehand, and in which case we should have an error there that grows linearly with the number of elements in the vector. We can alleviate this situation with pairwise summation, which is actually what base.sum implements. And this is a very classical divide and conquer algorithm where the vector is split into two halves that are summed recursively. And in terms of data flow, what this looks like is this sort of tree-like structure where at the first level all numbers are summed pairwise, and then all partial sums are summed pairwise as well, up until the end where we get the total sum. And in this case, we can expect the round-off errors to accumulate linearly with the depth of this tree. So that means a logarithmic growth with respect to the number of elements that we want to sum. And this is actually what we kind of see here, where we plot the relative error on the result of the summation as a function of the number of elements. And although the naive summation algorithm does perform a bit better than expected for smaller vectors up until 10,000 elements, eventually the error starts growing linearly with the number of elements, which is very much in contrast with the pairwise summation algorithm that always yields results that are as accurate as one could expect, which is with relative errors in the order of 10 to the minus 16th for the whole range of vector sizes. But all of this is only valid if there are no cancellations in these sums. And this happens in practice for a lot of cases, especially when all elements are of the same sign. And so the very practical case of this is when we are summing only positive elements. But as soon as we do have both positive and negative elements, then we have to worry about the condition number of the summation possibly getting larger. And so this is the relative error of the summation plotted against this time the condition number of the summation. And what we see is that as soon as the condition number starts growing, the relative error increases as well, up until a point where the condition number reaches something like 10 to the 15th, and the relative error is 100%, meaning that what we're computing is essentially garbage. And if we want to alleviate that, we can use compensated algorithms, which is actually what I'm going to be talking about today. And these algorithms allow to produce very accurate results up until the condition number is 10 to the 15th, and then the error starts growing again until the result is meaningless for condition numbers in the order of 10 to the 30th. In effect, everything happens with these algorithms as though we had computed the sum with quadruple precision numbers and then rounded the result in double precision. If we still want to go further and we have larger condition numbers, we can use exact summation algorithms such as the XSUM algorithm implementation that I mentioned earlier by Radford Neal, and this with such algorithms everything behaves as though we computed the whole sum in infinite precision and then rounded the result to double precision. But all of this comes with a price in terms of performance. So let's look at the performance of these algorithms. The summation is an algorithm that has linear complexity in the vector size, in the number of elements. So we could expect the time in nanosecond per element. We could expect it to be fairly stable. But it's not, because we have to account for the time it takes for memory, for data to come from memory to the CPU. So if we look at this region here, where the vector size is so small that all data can fit into the L1 cache, memory movement is so fast in this region that we're essentially measuring only CPU time. So we can see here that it takes around 0.1 nanosecond per element just to perform the summation itself. But as the data grows larger and larger, memory data has to come from the outer cache levels, level 2 cache, level 3 cache, or ultimately from the main memory. And this entails much larger waiting times, where the CPU is essentially waiting for the data to be available to compute on. If we look at the performance of compensated summation algorithms, what we see is that the baseline for small data that fit into the cache is much higher, because we have to perform more operations in order to get the increased accuracy. But as soon as the data grows a bit larger, then we still have to wait for data to flow from the outer cache levels or main memory to the CPU. And in such cases, the performance of the algorithms get limited again by the memory bandwidth, which means that the increased accuracy of such compensated algorithms is for free for large vectors and comes with a price only for smaller vectors. In this case, the Kahan-Babushka-Neumeier algorithm is it essentially behaves in the same way as the Ogita-Rumpo-Ishii algorithm. These are two different ways to compensate for the summation. But I should mention that this benchmark has been performed on an Intel Xeon high-end CPU, and you are not likely to observe the same results on your personal machines if you have a very standard laptop. In such cases, both of these algorithms should yield different performance, and you'd have to choose the most performant one for your machine. All of these timings should be taken in the light of the alternatives. And for example, the XSUM algorithm that I was mentioning earlier does yield even better accuracy, but it comes at a price of something like 2 to 5 nanoseconds per element. So we're still talking about yet another order of magnitude in the in the slowdown. Everything I've been mentioning so far applies for the summation, but also for the dot product. And so we also can compensate the dot product and have increased accuracy at the price of a factor 2 to 3 in performance for small vectors, and essentially for free for large vectors. So to sum this up, as a user, you'd want to use the pairwise algorithm implemented in base.sum if you know that your vectors are well conditioned, and this happens, for example, when all elements are positive. If your summation can become more ill-conditioned, then you might want to use compensated algorithms from the AccurateArithmetic package. And if you have very ill-conditioned summations, then maybe you'll have to use this XSum algorithm. For the dot product, you don't have much choice. If the BLAS implementation that linear algebra dot does not work in your case, then you'll have to go for the compensated algorithm that's implemented in this package. Well, so now let's try and look at how all of this works, and especially how compensated algorithms work. And the first stage that we have to understand here is a very basic building block that's called error-free transform, and I think it's better explained by examples. And so if I were to sum these two 32-bit floating point numbers, 10 million and 1.25, what I'd get with a standard addition as mandated by the IEEE 754 norm is this rounded result, which is 10 million and 1. And that's expected, and that's all fine. If I want more information, I can use instead of this standard addition, I can use an error-free transform. In this case, it's called toSum because I'm summing two numbers. And what I get out of it is the same rounded result, 10 million and 1, but I also get the associated round of error. So this is actually what error-free transforms do. They get you both the result of an operation rounded as usual, but also the associated round of error. And the way we can use that in summation algorithms to make them more accurate is as follows. If we remember what the naive summation does, we have this line of accumulations of all elements in turn into this accumulator sigma. And what we can do is replace all these individual accumulations by error-free transforms so that sigma becomes an accumulator of all first-order terms, like usual. But from each of these accumulations, we also get a round of error, an error term. And we can accumulate all these error terms into a second-order accumulator, that's called pi in this case. And the sum of sigma and pi gives us a much better result for the summation overall than sigma alone. And this is how compensated summations essentially work. But if we want them to be performant, then we have to leverage the vectorization capacities of modern hardware. And so if I look at, again, the naive summation in yet another way, what I'm essentially seeing is that this is a scalar. This accumulator is a scalar value that gets initialized with 0, and then I'm accumulating in it each element of the vector in turn. And in the end, this single scalar accumulator holds the total sum. But what I can do on modern architectures is work on packs of numbers all at once. So for example, let's say I'm on an architecture that allows working on packs of 4 floating point numbers all at once. I can replace my single accumulator by a pack of 4 accumulators that gets initialized with a pack of 4 zeros. And then what I can do is load from the vector a pack of the first 4 numbers and accumulate them all at once in the accumulator. And then I can load the pack of the following 4 numbers all at once and accumulate them all at once in the accumulator. And if I do that, I have an extra step to perform in the end, where all these individual accumulators that were packed together need to be combined and reduced to a single accumulator again. And the way this can be combined with compensated algorithms is if we manage to essentially define how this addition of 2 packs could be compensated, that is, how we could define error-free transforms between not only scalars but also packs of numbers, and how we could define a reduction of a pack of accumulators to a single accumulator without having any cancellations in these summations, or compensating for the possible cancellations in these sums. So that's essentially how vectorized implementations can be combined with compensated versions. And so how this is all implemented in AccurateArithmetic.jl? Well, the largest problem that we have is that we want to support 2 different algorithms, summation and dot products. We want to support a few different options for compensation, and we want to support both scalar implementations and vectorized implementations with maybe various SIMD width. And so that makes for an awful lot of variants of these algorithms to implement. But fortunately, the very classical architecture designs of Julia, especially revolving around multiple dispatch, these allow to essentially write everything once. So if I were to implement this very standard summation algorithm, then I could, for example, abstract this accumulation operation away by just defining a new generic function, addBang, and my naive summation algorithm would just require me to define a naive accumulator, a special type of this naive accumulator, a specific method for the addBang function that works for naive sum accumulators, and it tells how to accumulate a vector element into the accumulator. And this is a very simple transformation to do, but it allows me to very easily define new summation algorithms. For example, a compensated summation algorithm would only require me to define a new compensated accumulator and a specific method that would just define how the higher order terms get accumulated into a first field of the accumulator, and the second order terms get accumulated into a second field of this accumulator. So, while the same can be generalized so that, for example, this very simple loop can handle both summations and dot products, and in the end, we achieve a pretty good separations of concern where everything that's related to compensated arithmetic goes inside these accumulators, and everything that's related to performance and vectorization and loop unrolling and such things go into this one implementation of the loop. And of course, all of this is because we want everything to be very fast. And again, this is the same type of curves that I showed earlier, except this time it's benchmarked on a much more standard CPU. So this is more likely what you'll get if you test this on your laptops. And in this case, we see that the Kahan, Babushka, Neumayer algorithms performs a little bit worse than Ogita and Oishi. So that I would advise you to use this in your on your laptops, depending on what you have as a CPU. Anyway, as a conclusion, I'd like to say that again, what's very nice is that we can use very high-level programming techniques to implement complex algorithms easily and get as good a performance as, for example, BLAS does in C. And I'd encourage you to use the ready-made compensated algorithms from AccurateArithmetic.jl if you need them. And with that, I thank you for your time.